Alright, today's lecture is going to be on Earth's magnetic field, and we're going to be looking at the dynamo effect. We're going to be looking here, when we talk about the Earth's magnetic field, we need to make sure that we can recognize that a compass points northward because of Earth itself is a giant magnet. The compass dial, which is a weak magnet, aligns with the Earth's magnetic field. The magnetic poles of the Earth, however, do not coincide with geographic poles. They're not even very close, so when using a magnet we must take a magnetic declination. That's the difference between the geographic North Pole and the magnetic South Pole into account. The magnetic declination of Illinois is ironically near zero, so we will not have to change the compass dial to take this into account for what activities we'll do in class. So how does the Earth generate its magnetic field? Well, if we look at the infrastructure of the Earth, we could see that the liquid outer core is moving due to convection currents. The convection currents move charges around the solid iron inner core. As a result of this process, identical to the magnetism generated by moving charges around an iron nail, a magnetic field is produced. This process is called the dynamo effect. So how is the Earth's interior similar to an electromagnet? Well, the dynamo effect, the outer core, right? The outer core has these moving charges. And this electric current around, which is exactly like what we've defined electric current. So convection is moving these charges around a solid iron core, creating the Earth's magnetic field. This is the same concept here as a simple electromagnet. If we push current, right, cathode to anode, it tells me that here I'm moving current around this wire. This would be my magnetic North Pole, and this would be my magnetic South Pole. That both processes generate a magnetic field in the surrounding space. But if we look at this, we will see that the geographic North Pole of Earth is actually located near the magnetic South Pole. So if we look at the Earth as a bar magnet, right, if we would say that the North Pole is actually near geographic South, and the magnetic South Pole is near the geographic North Pole. So we need to make sure we keep that in mind. And we know this because we can use field lines, right? Field lines always point from the magnetic North to the magnetic South. And the Earth is just a really large but a very weak magnet. So Earth's magnetic fields. A compass dial is really just a small magnet that aligns itself within Earth's magnetic field. It always points in one direction. So our red needle is always going to point in one direction. When we move the base, we can travel on Earth's surface using it as a tool. Compasses have allowed humans to travel on Earth's surface and navigate over the oceans for over 1,000 years. And we do this because we can use this compass dial to get to one specific location just simply following the compass itself. So here are some pictures of the Earth's magnetic field. That the Earth is constantly streaming charged particles towards us. But the Earth's magnetic field kind of keeps us in this like safety zone. It's like a cocoon. So these are just all different pictures here. But what we have here is the Earth's magnetic field is definitely a shelter for Earth from dangerously charged particles. So the Earth's magnetic field, remember, the North Pole is located near geographic South, and therefore my magnetic field around it is the region in space in which the magnetic field or the forces are acting, right? Even though Earth's magnetic field is a weak magnetic field, it's still very large, that the magnetosphere protects Earth by inhibiting charged particle flow from the sun's solar wind from stripping off Earth's atmosphere. And the atmosphere and water are essential for life as we know it. Be sure to watch the last and final video, and I'll put it all together for you. That concludes this short lecture.